Welcome back to the Deep Dive, the place where we take a stack of challenging source material, strip away the jargon, and really find the nuggets of knowledge that genuinely reframe how you understand the world. Today, we are undertaking a deep dive into the very foundation of existence. I mean, the ultimate question of how life began and how evolution works, not just on Earth, but as a universal principle.
That's right. When most people think about evolution, they picture finches or maybe primates adapting to their environment.
Sure.
But our source material forces us to rewind much, much further. Before cells, before biology, before even chemistry as we know it, to generalize Darwin's theory.
Okay.
Our mission today is to explain how true complexity arose from simplicity, moving past that common phrase, survival of the fittest, to something much more foundational, the survival of the stable.
The survival of the stable. I like that.
Yeah,
And this deep dive, it follows an incredibly logical step-by-step argument.
it does.
We're going to trace the journey from the most basic stable structures in the universe through the improbable accident that created the first self-copying molecule, the replicator.
And then we'll get into the fierce, unconscious competition that drove selection in that molecular world, using criteria like longevity, fecundity, and fidelity.
And finally, we will arrive at the ultimate result of this long process, the invention of survival machines, which, spoiler alert, is us.
This is an intellectual shortcut, if you will. You are gaining a thorough understanding of the only scientifically viable explanation proposed so far for the origin of human complexity.
Wow.
It relies entirely on a progressive, cumulative sequence of events starting literally 4 billion years ago.
We promise you aha moments. Okay, let's unpack this foundational idea. So starting in the most basic place imaginable, physics.
Before anything else.
The universe, in its rawest form, is governed by a general law that favors the persistence of certain patterns. We are talking about the foundation of stability itself.
A stable thing is defined here very simply. It's a collection of atoms that is either permanent enough or common enough to deserve a name.
Okay, that's an interesting way to put it.
Yeah, it allows us to group together entities that, at first glance have nothing in common.
So we have two types of stability then. On one hand, you have unique, long-lasting structures, like the Matterhorn mountain.
The Matterhorn, exactly. That is a singular, massive collection of atoms that has persisted for millions of years. It's a great example of permanent stability.
It earns its name through sheer longevity.
Precisely. And then on the other hand, you have structures that are individually short-lived, but they come into existence so frequently that they deserve a collective identity.
Like raindrops.
Raindrops, perfect example. Each individual raindrop vanishes quickly, but the phenomenon of raindrops is highly stable and persistent.
So rocks, galaxies, ocean waves.
They all represent highly stable patterns of atoms to varying degrees, yeah.
And the stability, it's just inherent in the fundamental laws of physics and chemistry. It happens automatically. We don't need consciousness or life for it to occur.
Yeah, absolutely not. The tendency for matter to settle into stable configurations is the default state of the cosmos.
Okay.
Take a simple example, like a soap bubble. A bubble forms a spherical shape because that is the configuration that minimizes its total surface area for a given volume, which is the most thermodynamically stable state for that thin film.
Right, the lowest energy state.
The lowest energy state. If you take water into space, away from large gravitational forces, it naturally forms perfect, stable spherical globules.
That's the minimization of energy in action. And we see it in chemistry too, right?
Yes, in crystal formation, for example. Sodium chloride, common table salt, forms a cubic lattice structure.
Right.
And that's because that specific geometrical arrangement of sodium and chloride ions is the most stable and low energy way for them to pack together. This isn't a choice, it's a physical necessity.
And we can trace this physical necessity back to the very origins of matter after the Big Bang.
That's correct. I mean, since the formation of the first stars, atomic fusion has been operating on this same principle. Hydrogen atoms, under the intense heat and pressure of the sun, are forced to fuse into helium.
Why helium?
Because the helium nucleus represents a more stable, lower energy configuration than 4 separate hydrogen nuclei under those specific conditions. This process of forming more complex, stable atoms is literally how the elements that make up our bodies came into existence.
So if stability is the default and things naturally settle into patterns that resist breaking down, where does the complexity we see in life come from?
That's the million-dollar question.
Because a diamond crystal is stable, but it's just endlessly repeated and structurally simple. Life is anything but.
This is the critical transition point. Atoms link up to form stable molecules, but the sheer complexity of some modern biological molecules pushes the bounds of what we typically consider stable.
And we have a perfect example to illustrate this jump, the hemoglobin molecule.
Right, hemoglobin. The protein in our red blood cells responsible for carrying oxygen.
Okay.
It is constructed from chains of smaller molecules called amino acids. But look at the scale. One single hemoglobin molecule is made up of 574 amino acids arranged in 4 chains.
574, that's a lot.
It is. And these chains don't just lie flat. They fold and twist themselves into a massive, globular three-dimensional structure.
The source describes it beautifully. It's a structure of bewildering complexity, looking perhaps like a dense thorn bush.
It's a great description. But here's the profound implication that separates it from a real thorn bush. This is not an approximate haphazard shape. It is a definite invariant structure.
What do you mean by invariant?
I mean, every time your body creates a hemoglobin molecule, those 574 amino acids, given the same environment, will fold themselves into the exact same specific coiled pattern.
Yeah.
Every single time.
And how many times is this identical complex structure repeated?
Well, in an average human body, this single complex configuration is repeated identically over 6,000 million times.
That number it's just impossible to comprehend.
It is. But it means that, at a molecular level, the pattern is stable enough to be exactly reproduced at an astronomical scale within a fluid, dynamic environment like a cell.
So 2 chains of the same amino acids will always find the exact same stable, three-dimensional coiled pattern.
Always. It's physics.
So this is still pure physics and chemistry at work. The earliest selection happening in the universe wasn't about reproduction or competition in a biological sense. It was simply the selection of stable atomic patterns and the rejection of unstable ones, driven by thermodynamics.
That is the ultimate conclusion of this first part. Physics and chemistry select for stability.
Right.
But this realization creates a fundamental problem.
Right. Because if all stability explains is why hemoglobin molecules exist, it certainly doesn't explain why I exist.
Precisely. A man or a woman is composed of over 1,000 million atoms organized into complex systems, not just repeating identical molecules.
You could just shake them all together.
You couldn't. Trying to create a man by merely shaking the required atoms together in a cocktail shaker, even if you did this for a period of time far exceeding the age of the universe, would utterly fail.
Wow.
Random, undirected stability, dictated solely by thermodynamic necessity, cannot build an organism.
So the stability principle gets us to complex molecules, but it hits a wall before getting us to life. We need something more, a mechanism for progressive complexity. What's the bridge?
The bridge is Darwin's theory, but generalized. We need a mechanism where stability isn't static, where the stable structures can sort of improve themselves and increase their own stability over generational time.
Okay.
This process, which we call natural selection, takes over precisely where the slow, random building up of simple, stable molecules leaves off.
To find that mechanism, we have to travel back, what, 3,000 or 4,000 million years ago?
How about that, yeah. To the Earth's surface and peer into what is famously called the primeval soup.
Right. And this part of the story is necessarily speculative, isn't it?
It is. We have no direct record of the event, but the chemistry is highly plausible and widely accepted. We start with the conditions of the early Earth. The atmosphere likely contains simple compounds, notably water vapor, carbon dioxide, methane, and ammonia.
And the beauty of this account is that it's based on actual real-world simulations. Scientists didn't just hypothesize this, they went and recreated it.
They did. In laboratory flasks, they mixed these simple gases and provided intense energy, replicating conditions like powerful ultraviolet light from the sun or the electric energy of primordial lightning.
And what happened?
After running these simulations for a matter of weeks, the clear liquid transformed into a weak, brownish soup.
And what was in that soup?
Initially, they found simple organic molecules, most famously amino acids, the building blocks of proteins.
And that was a huge deal at the time.
A massive deal. Before these experiments, finding amino acids on a planet like Mars would have been considered conclusive evidence of life. But now we understand their presence simply implies raw materials, a bit of volcanic heat, and some energy from the sun or thunder.
That's a huge clarification, showing that the building blocks themselves are not life.
Exactly. They're just complex chemicals arising from non-complex chemicals. And importantly, later, more refined experiments also yielded purines and pyrimidines, which are the core building blocks of genetic molecules like DNA and RNA.
So the soup was getting thicker.
With all the necessary components for life, yeah. So these substances began to concentrate, maybe in drying tidal flats or small droplets, continuing to combine into larger and larger molecules.
And critically, that environment was fundamentally different from the seas today.
Absolutely. If you drop a large complex organic molecule into the ocean now, it is rapidly devoured.
Like bacteria.
Bacteria, fungi, other organisms. They're efficient molecular recycling systems. But 3 or 4 billion years ago, those organisms hadn't evolved yet. Large organic molecules could just drift unmolested through the thickening broth for vast stretches of time.
This environment, which allowed complex molecules to persist, created the necessary backdrop for what the source calls the exceedingly improbable event.
Yes. The truly transformative moment occurred when, purely by chance, a molecule formed that possessed an extraordinary, unique property, the ability to create copies of itself. This was the birth of the first replicator.
I think we need to pause here because our natural inclination is to say the chances of that are impossible.
And you would be right if you were considering the time frame of a single human lifetime is impossible in human terms.
Okay.
It's why you won't win the biggest lottery prize tomorrow. But when we transition our thinking to geological timescales, hundreds of millions, even billions of years, our everyday estimates of probability they fail us.
So we have to imagine playing that lottery every single week for 100 million years.
If you did that, you wouldn't just win once. You'd likely win several jackpots.
Right.
Over the immense, continuous span of primordial Earth, the seemingly impossible accident becomes mathematically inevitable. The replicator had to happen eventually.
Let's visualize the mechanics of this. How did this molecule, once formed, actually start making copies?
Well, the replicator acts as a template, or a mold. Imagine it as a long, complex chain.
Okay.
The primeval soup is filled with an abundance of smaller building blocks floating around it. These smaller blocks have a specific chemical affinity. They are attracted to and stick to certain parts of the replicator chain.
So the template automatically orders the raw materials in the surrounding soup.
Exactly. When the small blocks stick to the replicator, they arrange themselves in a sequence that precisely mirrors the original chain. They're lined up, ready to be fused into a new, complex chain. If that newly formed chain then joins up and detaches from the original template, you now have two replicators.
And we mentioned two different conceptual models for this process. One is simpler, like crystal formation.
That's the positive-positive model. The original chain, positive, attracts matching building blocks, and they form an identical positive copy. This is simple, but it has fidelity issues, much like crystal growth. A defect can easily propagate.
And the second model is more sophisticated, and it's the one modern DNA uses.
The positive-negative model. Here, the building blocks are attracted, not to their own kind, but reciprocally to a specific other kind.
A mirror image.
A mirror image, right. So the original replicator, positive, acts as a template to construct a completely different mirrored chain, a negative. Crucially, the negative chain then acts as a template to construct a new positive chain, which is an exact replica of the original.
So it's a two-step process.
It's a dual-step process,
Yeah.
template making, negative making positive, and it allows for much greater control, repair mechanisms, and structural fidelity.
Regardless of the exact mechanism, the outcome was revolutionary.
Absolutely. A new kind of stability emerged in the universe. Before this accident, no particular complex molecule was numerically abundant. They were all dependent on random chance. But the moment the replicator was born, it created a self-reinforcing loop.
It just took off.
Its copies spread rapidly until they dominated the seas, using up the small building blocks faster than they could be supplied.
The result was the sudden arrival of a large population of identical replicas, all descended from that single, ancient, accidental molecule.
And that right there is the birth of the self-propagating system. It sets the stage for selection.
The replicators quickly dominated, but as we know, no copying process is perfect. This is where the inevitable and crucial factor of error enters the story.
Imperfection is the engine of change. Even the most careful processes introduce mistakes.
Right.
Think about the days before the printing press, when manuscripts like the Gospels or historical texts were copied by hand. No matter how devoted the scribe, errors, misprints, transposed words, accidental omissions were inevitable.
And when copies are made from copies, which are made from copies, those errors don't just accumulate, they propagate through entire lineages.
Exactly. They become cumulative and can become deeply ingrained in the resulting population.
And there's a great anecdote about this in the source material, isn't there?
There is a wonderful one regarding the Septuagint. The Septuagint was the earliest Greek translation of the Hebrew Bible. The original Hebrew word used to describe the mother of a future savior figure meant young woman.
Okay, young woman, pretty straightforward.
Right. But the translation process introduced an error.
What happened?
The Hebrew word was mistranslated into the Greek word meaning virgin.
Oh.
This seemingly simple scribal error, propagated through generations of copies and subsequent cultural interpretation, gave rise to the prophecy that a virgin shall conceive and bear a son.
And that's a huge deal. Here's where it gets really interesting. A single copying mistake didn't just corrupt the text. It fundamentally altered the entire trajectory of a major religious and historical narrative.
It shows the terrifying power of error propagation over generations. It's proof that miscopying can literally start something monumental. And erratic copying in the early biological replicators was not just a side effect, it was absolutely essential. Some of those copying errors gave rise to improvement, a higher level of stability or a faster copying rate.
Which leads us to a bit of a paradox, because while evolution needs mistakes, we know that modern DNA is astonishingly faithful, far more accurate than any human scribe.
Far more.
The original replicators were likely much more erratic, but selection pressure would have immediately started favoring the accurate ones.
This is the crux of molecular natural selection. As miscopyings occurred, the soup filled up with several varieties or strains of replicator molecules, all descended from the same ancestor, but slightly different.
And there were three key properties that decided which ones won.
We can identify three key properties, yes,
Right.
that immediately determined which varieties flourished and which were destined for extinction.
Let's dive into those three evolutionary trends, starting with the most basic one, longevity.
Longevity simply refers to how long an individual molecule lasts. Molecules that were chemically more stable and lasted longer had more time to make copies of themselves before they broke apart.
Okay, that makes sense.
It conferred a clear numerical advantage in the population. The stable ones persisted, inevitably leading to an evolutionary trend toward greater molecular longevity. They were the slow, steady winners.
But the next factor, fecundity, often trumped longevity.
Fecundity, it's the speed and rate of replication.
Right.
Imagine replicator type A lasts a year, but only manages to copy itself once a week. Now, consider type B, which only lasts a month, but copies itself once every hour.
Type B is gonna win, hands down.
Type B, the faster copier, will quickly dominate the population, even if its individual lifespan is significantly shorter. Therefore, the evolutionary trend was strongly pushed towards high fecundity. The winners were the ones who could pump out copies the fastest.
And the third property, which directly addresses the paradox we mentioned earlier, is copying fidelity, the accuracy of replication.
This is the subtlest and perhaps most powerful trend. Imagine two varieties, X and Y, which replicate at the same speed and last for the same duration. The only difference is that X makes a copying mistake on average every 10th replication, while Y makes a mistake only every 100th.
Y, the more accurate one, will become overwhelmingly more numerous.
Exactly, and the reason is brutal. The inaccurate variety, X, loses not only the errant children themselves, the molecules that are malformed and can't replicate, but it loses all their potential descendants.
Wow.
Every time X makes a mistake, that lineage is potentially truncated. Selection acts fiercely to preserve the successful structure most faithfully. It favors high fidelity, driving the whole population toward accuracy.
So we are left with this deep paradox. Evolution, by definition, is change, which requires error. Yet natural selection, the mechanism of evolution, actively drives the system toward perfect, unchanging accuracy. Why did the replicators ever evolve beyond simple, highly accurate molecular chains?
That is the essential philosophical insight here. It highlights that the process is not driven by desire. Nothing, not the molecule, not the gene, actually wants to evolve. Evolution is simply something that happens, willy-nilly, as an unintended consequence of survival. It occurs in spite of the replicator's attempts to achieve perfect, unvarying copying.
So the reason we see complexity today is because some of those mistakes, even though they were rare and selected against for the most part, occasionally led to a molecule that was so much more successful at survival in terms of longevity, fecundity, or fidelity, that the benefit outweighed the cost of the initial error.
That's the cumulative principle in action. If we were to analyze the soup at two different points in time, separated by 1 million years, The later sample would contain a dramatically higher proportion of varieties possessing superior longevity, superior fecundity, and superior copying fidelity.
And that's natural selection.
That's natural selection, divorced entirely from any notion of biology, consciousness, or fitness in the conventional sense.
Before we move on, let's revisit the idea of labeling. The source points out that we've discussed these molecules for ages, but haven't used the word living. Does it matter?
The short answer is no. It absolutely does not matter. The word living is just a human tool, a label we use to delineate a boundary. Whether we decide the original replicator molecules were living or not, the facts of their origin, their replication, and their selection remain unchanged.
They were the ancestors.
They were the undeniable ancestors of all life. It's a great reminder to focus on the process, not the vocabulary.
As the replicators multiplied exponentially due to their newfound success, the environment changed dramatically. The raw materials, the floating building blocks, and the primeval soup.
They went from abundant to being a scarce and precious resource.
This is a huge shift.
This environmental shift is the critical link to Darwin. This created the classic Malthusian struggle for existence. Different strains of replicators, some highly fecund, others long-lived, began competing fiercely, though unconsciously, for the finite supply of building blocks.
This struggle was relentless. We're talking molecular warfare here.
We really are. The less favored varieties, those that were slower or less accurate, found themselves numerically disadvantaged, and their lines went extinct.
And this wasn't conscious.
The struggle wasn't based on conscious rivalry or hard feelings. It was purely chemical. Any miscopying that created a new trait, either a new, higher level of chemical stability for that variety or a new way of actively reducing the stability of rivals, was automatically preserved and multiplied.
This marks the beginning of the molecular arms race. The methods of increasing one's own stability and decreasing the rival stability became more and more elaborate.
It kicked off offensive strategies.
Right.
The first major strategic leap was the invention of molecular aggression. Some replicators stumbled upon a structure or a chemical reaction that allowed them to literally break up the molecules of rival replicator varieties.
So they weren't just waiting for building blocks to appear, they were stealing them.
You're stealing them. These were the very first proto-carnivores.
Proto-carnivores. I love that.
Absolutely. And think about the elegant efficiency of that strategy. A replicator that could chemically dismantle its rival achieved two immense evolutionary advantages simultaneously. First, it gained a new source of fuel and building blocks.
And second, it eliminated the competition.
It eliminated competition by destroying a rival lineage. It's a perfect selective advantage.
So in response, the pressure on other replicators to defend themselves must have become enormous.
It did. The next major strategic leap was defense. Other replicators developed specialized chemical means to resist being broken apart. More importantly, they began constructing physical barriers.
How?
They started building a protective coat or a physical wall of protein around themselves.
That sounds suspiciously like the beginning of a cell.
It is the moment the first living cell appeared. This protective action, the construction of a permanent defensible boundary, fundamentally changed the game. It marked the pivotal transition point in this deep dive. Replicators began not just to exist, but to construct for themselves containers or vehicles for their continued existence.
And here is the key terminology that defines the rest of the evolutionary story. The birth of the survival machine.
The birth of the survival machine. The replicators that survived were the ones that managed to build the most effective shelter.
And those early machines must have been very simple.
The earliest survival machines were undoubtedly simple. Perhaps nothing more than a basic lipid coat enclosing the replicator chains and some necessary tools. But as molecular rivals continued to develop better offensive weapons, the survival machines had to become progressively bigger, more complex, and more elaborately defended.
It was an escalating architectural and engineering project.
A 4-billion-year-long project. This leads to the staggering implication that everything we see in the biosphere, including us, is merely an extension of this initial defensive strategy.
That's incredible.
That's the great synthesis. The fundamental conflict remained between the replicator molecules, and that conflict drove the continual engineering and improvement of the vehicles they inhabit, the survival machines. What started as a simple protein coat eventually evolved into systems capable of locomotion, sensation, and behavior, designed to protect and propagate the information sealed inside.
So, the evolutionary journey is a story of construction, driven by stability and competition. We went from stable atoms to complex, thermodynamically stable molecules like hemoglobin to the accidental self-copying replicator.
which then engaged in unconscious competition that culminated in the engineering of these elaborate vehicles, the survival machines.
Yeah.
So if we look at that grand sweep of time, we have to ask the final question. What was the fate of those ancient original replicators? Did they disappear when they enclosed themselves in those first cells?
Logic would suggest that perhaps they burned out or, were superseded by the complexity they created.
On the contrary, they did not die out. They didn't vanish. They are described, and rightly so, as past masters of the survival arts. They simply evolved their strategy. They gave up the cavalier freedom of floating loose in the primordial sea a long, long time ago.
They adopted a new, far more secure lifestyle. This is the punchline, the big reveal that connects 4 billion years of history to you, the listener, right now.
They now swarm, not individually, but in vast, intricate, organized colonies. They are safe and secure inside gigantic lumbering robots, sealed off from the outside world and manipulating it only by tortuous indirect rope.
And these gigantic lumbering robots, these highly complex survival machines, we are them.
We are them.
They built us body and mind cell by cell. The ultimate rationale for our existence, our health, our survival, and our reproduction is simply their preservation.
These ancient replicators have come a very, very long way. They're no longer simple chains of purines and pyrimidines floating in a warm broth. They are structurally advanced, highly accurate information packets. Now, they go by the name of genes, and we are their survival machines.
So, what does this foundational knowledge mean for you? It means the story of evolution is fundamentally a story of self-interest and information persistence. The laws that govern your behavior, your instincts, and your entire complex anatomy trace back directly to the molecular selection pressures of longevity, fecundity, and fidelity that occurred in a brown, weak soup billions of years ago.
And that leads us to our final provocative thought for you to explore on your own. We discussed earlier that labeling the original replicator as living or non-living is irrelevant. The process remains the same.
Right.
Consider how our modern tendency to draw sharp distinctions, like conscious versus unconscious or man versus machine, might similarly prevent us from seeing the underlying universal laws of stability and replication still at work across all systems, whether biological or technological. Where do you draw the line, and are those lines truly meaningful?
A profound challenge to our understanding of the world. Thank you for joining us on this deep dive into the foundations of evolutionary thought. We'll see you next time.